Good morning or good afternoon, depending on where you're joining us from, and welcome to today's webinar. I'm Cess, your moderator from Business Review, and it's truly a pleasure to have you all here. We're delighted to have our wonderful sponsor, INNIO Group's Jenbacher, with us today, who'll be presenting this webinar titled Green Hydrogen for E-Mobility with Jenbacher. Let me introduce our esteemed guest speakers for today. We have Andrea, Senior Business Development Manager at INNIO Group's Jenbacher brand, and Stefano from the University of Rome Tor Vergata. Now, before we dive into the content, let me quickly walk you through our webinar platform. This webinar is browser-based, so if you get disconnected for any reason, just refresh your page or click the link in your email to hop back in. Also, today's session is being recorded, so you'll be able to access it on demand later. If you have any questions during the webinar, we'd love to hear them. Simply type them into the questions widget and at the top left-hand corner of your screen and click submit. We'll save some time at the end for a Q&A session to go over your queries. Don't forget to check out our related resource widget for more helpful materials. And after the webinar, we'd really appreciate it if you could take a moment to fill out the surveys to share your feedback with us. If you need any technical assistance, the help widget is available to support you, and you can also resize or maximize any of the windows on your screen for a better view of the slides. Now, without further ado, let's give a warm welcome to our first speaker, Andrea.
Yes, good morning, good afternoon, or good evening. We have a very wide audience today for this webinar, and we are very happy that today we can show you our latest work that we have done. So I'm very happy to be also together with Professor Stefano Mazzoni from the University of Rome, that has been very helpful in providing us a lot of inputs and work together in order to reach some achievement on this energy storage solution. So the starting point of today is to illustrate you the content of our latest white paper that has been published very few days ago. And we will provide you at the end of the presentation also the information how to download this white paper and where to find it. So the starting point of all the story is from where we, let's say, take the energy in order to bring the power to the batteries for the electric vehicle. And we have seen a lot of issues and a lot of troubles coming from the infrastructure. So as you can see in this slide, this is only a small collection of inputs that you can find in the news around the globe. What is the biggest barrier for the commercial EV charger deployment? And this is the infrastructure. So based on this challenge, we wanted to, let's say, do a study on a possible solution. And the possible solution starting point is nothing really new, because if we look on the left side in this picture, here we have the old system, or let's say the actual system that has been used since a century or more, where the oil coming from a refinery is brought to the fueling station by means of a truck, and this oil is provided to the cars. And the concept could be, let's say, the same, but instead of bringing oil, we can bring hydrogen or green hydrogen to the EV charging station and bring this hydrogen inside a system that converts this hydrogen into electricity without any stress to the infrastructure. So what we will see today, and I will go through brief agenda, is some information, some background information in order to understand a little bit better which are the numbers behind the future of e-mobility, and what are the solutions that can be, let's say, offered in this kind of energy storage requirements, and the role that our products can play in this future world. And then we will deep dive into the case study, which is actually the core of our white paper. So this is a real study to power an EV charging system with a size of 1 megawatt with hydrogen. And then there will be time for your questions. So you can use the system that has been just explained by Cess, and you can put your questions and we will answer to them at the end of the session. And of course, we want to get your feedback because we want to listen for you what you think about this idea and if you see any potential way to work together, because at the end of the day, what we want to do is to help you to solve the issues that we have and to work together in this direction. Right. So having said that, let me start. And I would like to start with this EV charging capacity outlook. This is an outlook that has been published very recently by the IEA, the International Energy Agency. And you know they have two different levels. This is the steps, the stated policy scenario, which means what would happen in the future if the policies which are deployed by the government will remain the same like today. And the APS is the announced pledge scenario, which shows us what will be the market if there will be, let's say, an aim from the politician to reach the 2050 target. What we see in the y-axis, and this is what I want to highlight here, is the scale of the installed capacity for the vehicle charger from 2023 to 2035. Today, we are at the level of less than 0.5 terawatt globally. But if we go to 2035, this explode literally to more than 4 terawatt hour. So we can really understand that this is a huge potential market, and this is something really that doesn't depend on the policies for the 2050, but it is really something that will happen beside the climate things, because this is something that we see ongoing more and more. And in this study, there are also other information which I will try to summarize, also to provide us a little bit of more context. So the segment growth of the EV charging is growing and is expected to reach 17 million by 2024. So this is the number of car, means that one car over 5 sold globally will be electric in 2024. And this is already a 45% market in China, 25% in Europe, more than 11% in the US by the end of this year. This impact, of course, the energy sector, because, of course, on one side we reduce the oil demand, but on the other side we have to find other ways to provide the energy to these cars. So we have also identified key markets, key segments for EVs, like China, where 60% of the global sales is going to, and Europe with 25%. There are many policy measures and incentivation for the EV and battery manufacturing. For example, there is the production-linked incentivation scheme in India. There are, of course, subsidies coming from the US Inflation Reduction Act. And this is also something that applies to the battery production and to the supply chains. There are investments in EV and battery manufacturing for almost 500 billion from 2022 to 2023 globally. So there are numbers that are really, really impressive. There are also emerging economies which are becoming important in this market, for example, in Southeast Asia. And in addition to that, what we see that is a very big trendy topic is the global number of installed public charging points is increasing by 40% in 2023 compared to 2022. But the aim is to, let's say, increase sixfold by 2035. And then the fast charger. So this is also one of the reasons that draw our attention to the fast charging solution. We see that according to this IEA report, the fast charger will be developing much faster, of course, than the slower chargers, and also because there will be more electric heavy-duty vehicles hitting the road, and then they need a dedicated flexible charging for them. And all of that will have a significant implication for expanding and operating the electrical grid. And here I leave now the stage to the Professor Stefano to complement with additional information. Please, Stefano.
Good afternoon, everyone, and good morning and good evening to the other part of the world. And thanks, Andrea and INNIO, for the great opportunity to be on the stage today. And I will continue taking from the last concept about the fast charging that Andrea mentioned before, because we should always remember that one of the main problems when we deal with the relying on electric vehicle infrastructure is the fact that there is a very high power demand when you need to recharge a battery with a certain capacity that is an energy in a short time. And when you think of the power side, so the design of a power system capable to support multiple and concurrently charging electric vehicles, you can imagine how the complexity of the system increase. This is because you need large cable, you need to manage the heat management part of the pipe of the electricity, and all these aspects brings to challenging cost and investment strategy to follow in order to make the infrastructure robust and resilient. Another aspect that is important is that this fast charging requires high performance in terms of availability and reliability. And of course, for ensuring that backup solution and energy storage solution can play a pivotal role in supporting the transition. And the advantage, the key competitive advantage that we foresee in hydrogen integration in the electromobility infrastructure is that they are not just a storage solution, so they are not just an hardware, but they are also an energy carrier. That means that they are easy to transport from one side to another. And at the same time, they can be seen as a storage solution for short, medium, and long term, while electrochemical energy storage, and I will deep dive into more details later on, has some problematic approach related to the availability of the material to build up the batteries, and as well that once they are located in a location, the battery is a static energy storage solution. So the concept of integrating hydrogen as an alternative energy carrier and storage solution for electromobility is something fundamental to support self-sufficiency and sustainability power supply for electric vehicle infrastructure. And we understand, together with the number that Andrea showed before, in terms of which will be the installed capacity in terms of terawatt for the power required by the infrastructure of electromobility, which is the role that energy storage has. So here is a interesting chart taken by Roland Berger report of 2022, where on the x-axis there is a storage capacity, and on the y-axis is the discharging time. And you can see that we move from a few kilowatt hour, typically of flywheels and small batteries, up to terawatt hour, where hydrogen and synthetic natural gas are playing the pivotal role in exploiting the solution. So you can clearly understand that the first differentiation between the former and the latter technologies, that one relies on hardware, so like flywheels and battery. The one in the middle, like pumped hydrogen storage and compressed energy storage, use a working fluid media to perform the storing process, while above 1 gigawatt hour, looking to the capacity we discussed before, energy carriers such as hydrogen and synthetic natural gas allows to look for a longer and seasonalities also storage solution, but especially for a more consistent discharging time. That is what we need when we deal with half an hour to 1 hour fast charging for the electric vehicle infrastructure. So you can see that clearly a solution based on energy carriers can supply and support the trend of the electric vehicle infrastructure forecasted by EA to rise up to 5 to 10 terawatt of installed capacity in the next decade. And now I give back the word to Andrea.
Thanks, Stefano. Thanks a lot. So now, before we start with the white paper case, I want to show you very briefly what was the system concept that we have developed. In order to understand really how we can create a virtual pipeline and bring hydrogen to power the EV site, we need to start with the requirements. And when we say requirements, we mean how many cars we want to charge, for how much time, and especially what are, let's say, the cases and the statistics that could help us in order to make a proper simulation of a business case. So we wanted to, let's say, study a little bit in details. It's not easy to find literature about possible loads of this kind of charging station. But we have been, let's say, trying to make an iterative process running through a technical feasibility and a viability in terms of financial. So we have done different iterations in order to size, to find the best sizing of the entire process in order to stay within a megawatt size, which is for us, in our opinion, a middle size that could be helpful to understand the business case and also, let's say, develop it for other sizes. And then what we have, let's say, target was also other energy consumer in order to provide a better financial viability of the entire concept. So we will see later on the details, but before we go with the details, let me introduce the core of the idea. The core of the idea is the Jenbacher engine, which is capable to run with 100% hydrogen and can provide power generation and cogeneration and trigeneration as well. And I would like also to show you this brief video, which show very clearly the product that we are talking about. So this is a containerized unit of 1 megawatt size producing electricity with hydrogen. It is a plug and play solution. Here you see the video from our factory in Jenbach, where we have tested this solution some months ago. So it's quite a recent project. And yeah, so many details, some that are familiar with our products know, but here really you just need to plug the hydrogen source and the electric cable, and you have a turnkey solution that can really very fast provide the solution to the infrastructure, because really in few months you can go from the start to the deployment very easily. And this is our portfolio. So, you know, all the Jenbacher units are ready for hydrogen. We have a different size. We start from the smaller engine, the Type 2, which is more or less on the 200, 300 kilowatt size. And then we move up to the Type 3 and the Type 4. The Type 4 is the one that we have been using into this modeling, and especially the Type 420, so the 20 cylinder here. And here we have 3 categories for each product of ours. So the category A is the standard engine that is already available with capability to run up to 5% of hydrogen in the pipeline gas without any modification. And there is also the optional standard product, which could run up to 25% of hydrogen in the pipeline gas. Then we have the second category, which is the most interesting one in terms of this timing of transition from the natural gas to the next phase. And this is the category B, and this is an engine that is capable to run from 0 to 100% in volume of hydrogen. And you can see here that the Type 4, so the Type 4 which goes from 500 kilowatt to 1 megawatt is capable to run 100% hydrogen. Or as well, which is the category C, we can run up to with only pure engine, so hydrogen engine. So in category B, you can run with 2 fuels, dual fuel, hydrogen and natural gas. And with the category C, you can run only with the pure hydrogen. And as well here, another slide in order to illustrate a little bit better what I just said before. So this shows really the demand from our customer when they want to, let's say, go to an asset that is capable to run in different solutions, but with the same asset. So they can start with a natural gas asset capable to run up to 5% volume of hydrogen. And then the same asset can be with a low-cost package converted to ready for 25% hydrogen. And then with another package of modification can be switched to a hydrogen asset. So here we see really the flexibility of the same asset to run through the demanding period of the transition that we are facing today. And last but not least, I would like to show you some of our projects worldwide with hydrogen. And in particular, I would like to mention the Answerk in Germany, which was the first plant that has been converted from a natural gas source to hydrogen source. So this was an existing engine that was running on natural gas. And the customer wanted to change it to hydrogen. And another one that I would like to briefly mention is there is RAG, Austria, which is the first European cogeneration plant running on hydrogen. And in this project, our customer is producing hydrogen during the summer period and is storing this hydrogen in an underground storage to use this summer sun to power the winter energy. So this is really the concept that Stefano was illustrating to us before, that we need this kind of energy vector in order to use the energy from the renewable when there is no possibility to do as well. So now I think we are ready to deep dive into the case study. And again, we have seen this overall concept. So we will start now with the first flag, the start requirements, where everything is starting from. So the number here we are showing you is that we are targeting 8 of charging station of 125 kilowatt of power. And making, let's say, some evaluation on the loads, we have been working together with software for simulation, which is called XLD. And with this software, we are able to simulate EV charging demands. And we are able to make the design of the load curves according to potential usage of the charging system, of the charging of the vehicle. So at the end of the day, after many iterations and many assumptions, we have ended up with a load curve, which is here one simplified version. And we end up that we can charge a number of more than 40,000 cars per year, assuming that they have an average 60 kilowatt hour battery capacity. So in total, we are summing up to more than 2.4 million of kilowatt hour, right? So this is the starting point of our assumption. And now I leave the stage again to Stefano to proceed with the technical.
Yeah, thank you, Andrea. So after having somehow, I deep dive a bit more into the, let's say, mathematical formulation of the problem, but then I will sum it up in a more practical way. After having set the demands, so how much electricity we need to satisfy with the green hydrogen generated, we need to understand from the technical perspective and from the economic perspective, which are the optimal configuration of the renewable energy source, of the backup and the energy storage, plus the transportation capacity that allow the solution to be economically viable, both from the end customer perspective, both from whoever generate the green hydrogen. So for doing so, we have developed together with Andrea and INNIO a model that we run to validate some of the data given available in the literature to understand how we could have supply concurrently electricity for electric charging at high tension, so for fast charging, and then given the capacity of cogenerating of the CHP unit equipped with the INNIO engine, also additional assets such as heat and cooling for energy consumers. So the results of the optimization, that was a constraint optimization based off a mixed integer linear programming approach, we were able to establish the capacity of the solar field that was in the size of 12 megawatt. And the electricity generated by the renewable energy resource, as you know, is intermittent. So we can somehow supply the excess of the electricity to the grid when not needed. We are able to charge an electrochemical energy storage of 8 megawatt hour. This is the results of the optimization. And how we establish this number? We establish this number because we need to be able to feed and electrolyzers with a capacity of 70 kilogram per hour of hydrogen. So this is the constraints that we had from the optimization perspective in order to satisfy and supply the all electricity demand for charging the up to 40,000 vehicles in a year that Andrea mentioned before. What we did was, on the first stage, we used the data given by XND, that is a software platform used by Andrea for running the preliminary simulation to understand the solar availability in the field. And then we integrate with some tool that we adopt in the university, that we develop internally in the university, on an optimal dispatching profile in which we understand how we should operate. Here is a bit light, but there is a light gray line that shows which is the state of charge of the battery, in order to guarantee that the electrolyzer can work almost at nominal load, because the electrolyzer suffers from part load operation, for the largest hour of the day possible, and simultaneously to be able to export the electricity when the grid requires it. So as a result of the optimization, we were able to supply a constant load almost to the section of compressing hydrogen that was designed to be a 500 kilogram hydrogen storage tank with a pressure between 30 and 250 bar to be delivered by the compressor. And at the end, to deliver the hydrogen produced in the site A to the site B, that in our assumption was about 2 kilometers far from the electric vehicle station, we needed to adopt a virtual pipeline. So basically, we're relying on H2 truck. We make some calculation, of course, because it's fundamental to account for the embedded emission in the transportation process, given the fact that they run on diesel fuel, gasoline fuel, and to account also for the cost of the transportation that should be at the end of the day included in the levelized cost of hydrogen evaluation. And by the assumption that we received by a vendor, Andrea will give you more details later on the details of the H2 truck company, we're able to calculate almost 1.4 euro per kilogram of hydrogen of transportation with an emission below 0.4. This number is very important, and later on we will show how, because a number in that order of magnitude would allow incentivization mechanisms in other parts of the world. I give you back the word, Andrea.
Yes, thanks, Stefano. So if we look here to the truck that we see here represented, what we wanted to do is to ask to a specialized company, which is called PRF, to make a study for us regarding this specific case, in order to provide us the best solution to transport the hydrogen from the site A to the site B, which is 200 kilometers away. So what they did was they calculate the buffer storage, they calculate the compression system, and they calculate how many trailers are needed. So we have 2 trailers plus 1 strategic. And with this configuration, we are able to bring the hydrogen in the quantity which is needed by the load that we have seen in the previous slide. So this calculation was really, really important in order to check what are the hydrogen transportation costs. And of course, we have also done some literature research in order to see if our assumptions were correct, and we see that these numbers are aligned. Again, I would like that to remind that all the detailed information are written in the white paper. So here, for the matter of time, we cannot go really into all the details. But if you have the pleasure to read the documents, you will find all the answers to maybe some question that you could have. I would like to highlight that you have the possibility to make your question in the system of the broadcast. So you can go to the survey and input your question, and we will be able to answer all of your questions at the end of the webinar. So when we bring the hydrogen to the site of use, here we find the engine. So the engine that we have seen before will take the hydrogen and will produce the electricity for the EV charging. In the simulation model, the simulation suggests us as well to include a small battery for taking the fluctuation of the EV charging load curves. So here it is an additional little battery, which helps us to stabilize the flow. And yeah, so what we have to do is to comply with this load curve. In addition to that, we want to use all the benefit of the engine as well on the heat side. So in our assumption, we are thinking to deploy this solution to an EV charging station, which has also some other energy consumers like a little shopping mall or restaurants and so on. You know that there are small and big charging areas. So this is more targeting a big size charging area with a lot of facilities. So they have heat demand. And what we have done as well in the simulation was to include an absorption chiller and a peaking boiler that is running on hydrogen as well in order to fulfill the load from the thermal side of the mall or of the charging station altogether. So here we want really to squeeze out from the engine all the efficiencies possible, because this hydrogen that we are delivering is very precious and is very expensive, so we don't want to waste anything from that. So the efficiency for us was really an important pillar to highlight that still, you know, the efficiency plays a big role even in the decarbonization path. And then what we wanted to do was to see if this idea technically developed was also financially viable. And we will see now how the number will come together. So in terms of cost, we have used cost from the market, and we wanted to give real figures for installed equipment. So we were considering CapEx and OpEx for a period of 15 years, because the 15 years is the normal time of kind of project with cogeneration unit. So we wanted to make altogether cost for capital expenditure and operational expenditure in one line, and what it end up, if we sum all the items in this simulation, we reach a number of 25.5 million euro for the 15 years. So this is one important baseline. You might think it's a big number, it's a small number. We will see it later. And here I, again, hand over to Stefano.
Thank you, Andrea. And the first evaluation of the capital expenditure was fundamental, because for accounting the overall cost of the hydrogen generated from renewable energy source to the electric vehicle infrastructure, we need to account for all the costs, so including capital cost, operating cost, and the amount of hydrogen produced. Here we make a brief sum up of which were the constraints. So we needed to deliver about 2.5 million kilowatt hour of electricity for the charging station. We account for above 40,000 vehicles. We have roughly 2 million kilowatt hour of heat generated by the cogeneration unit. That leads to almost 1 million revenue or saving if you compare with a typical district heating price of 4 cents of euro for kilowatt hour for generating or for purchasing heat. And we arrive to the cost of the green hydrogen in a range between 10 to 10.5 euro per kilogram. The question could be, is this price high or is this price low? This is something that is very interesting to discuss, because if we would have run a simulation, and we did this during the project with Andrea, just for the month of August, this cost would have been of around 6. If we would have run that only during February, the cost would have been around 14. So the message behind is that this is a price that accounts for all the seasonality that we encounter over a year in a continental climate region like Europe, and is a price that from our analysis makes still the solution viable. This is something very important to say, because we provide for a solution with almost 92-93% decarbonization when compared to the traditional electricity generated by the grid, and we were able to make the cost of the charging station of about 1 to 2.12 euro per kilowatt hour. That is comparable with what is the price of the charging station, especially the fast charging station in Europe up to date. So this is something very interesting and very important to remind, because all the figure that we calculated take their foundation based on existing technology, on market available components, so their solution can be really implemented with this cost. So I give back the word to Andrea.
Yes, thanks, Stefan. I will take exactly from here, because when we look to the number, we say we have 1.1 in average euro per kilowatt hour at the charging station. If you look on the European Alternative Fuels Observatory, you find all the prices of the EV charging station. And what we have plotted here is the example for Austria, because the Jenbacher is from Austria, and the minimum price that Austrians paid for charging the car was 0.09 euro cent, which is very, very small. But the maximum price was 1.83. So this is a real number, which I mean, it is higher than our calculation, which is 1.1. So what we want to say here is that we are proposing a solution that have this final number that has to be paid by the charger, but this brings them half an hour for charging the car with green energy, with a very, very small CO2 quota. And then the topic is what happens if some incentivation scheme apply. And we have done a lot of also additional reflection on that, and you will find in the white paper how does this simulation result can change. And we will see a little bit this later on. And I think now is your turn, Stefano, to proceed.
Yeah, thanks, Andrea. So basically, following up on what we said at the beginning and what just Andrea said, there are schemes that allows for getting some incentives, and these numbers are reported in the white paper. But the message behind this chart is that we propose sensitivity analysis on net present value. That means that we account for capital investment, operating cost, and the equivalent cost of the hydrogen to evaluate the viability of the investment. And we propose in this case scenario four scenarios. So one is where we are able to get some incentives of around 2.5 to 3 euro per kilogram of hydrogen and maintaining the selling price of the electricity at 1.1 euro per kilowatt hour. And you can see, just let me get the pen, that we have a payback time in the order of 4.5 to 6 years. Then we make the other scenario that is the worst case scenario, in which the cost of hydrogen is the highest without incentives at all, so 10.5, and in which for making the viability of the solution below 10 years, we need to increase a bit the cost of the selling of the electricity for the electric vehicle of around 1.2, and the payback in between 8 and 9 years. Now we also explore a case scenario typical of what can be Euro zone incentive mechanism, in which we can have a 9.5 euro per kilogram of hydrogen cost and 1.2 euro per kilowatt hour, and we can shrink down the payback period of around 7 years. And then we have the most promising scenario, in case we can reduce a bit the cost of the generation and access to different kind of incentivation schemes, in which we can keep the same payback period of 9 years, but helping the end customer to lower down the price to a cost of 90 cents per kilowatt hour. And this is really a feasible target from our perspective, because it is what the technology is going to move forward at. So the capital cost will reduce. For sure, the incentivation mechanism will play an important role, but the solution can be really meeting the up-to-date price for the fast charging station. And this is something that you can find more details. Here we have just some numbers that they already discussed. And I think that I leave the word to Andrea to sum up all the finding of our white paper.
Yes, thanks, Stefano. I think exactly we reached the end of our case explanation, but we would like just to give a little bit of an overview of the overall system. So you see here in this schematic all the information from the start requirements on the hydrogen production site, on the virtual pipeline for the hydrogen supply. We have discussed why we have chosen this kind of solution, because the system was providing us different iterations and in terms of economics, in terms of technical solution. And what we wanted to highlight is that the consumption on the site must be, let's say, as much efficient as possible in order to maximize the income and the potential return on this kind of investment. So finally, the viability, even if the cost to make everything together is expensive, it does not consider any additional cost for the infrastructure or any delay that someone has to wait for the infrastructure to be ready. So the fact is that with this kind of configuration, you can produce green hydrogen in a location which is where it is more convenient, because normally the routes of the cars are already defined and they are already very busy, and there is no space enough to locally produce the green hydrogen and to supply with a very short connection the hydrogen to the point of use of the cars. We don't need much high pressure to transport it. We just need 2-3 vessels in order to make 1 megawatt. And everything together, it gives us an interesting outcome. And this is an outcome that considers the state of the art of today. So we know that this simulation has been done in Europe. We know that the efficiency of the photovoltaic and production in Europe is not the best one that we can find in the planet. We know that there are ongoing studies around the world in order to produce clean hydrogen and transport it, for example, as a clean ammonia to the point of use at a level of price that is targeted to be much, much lower than the 10 euro per kilo that we have been assuming. And we had the time to do also some financial evaluation. What happens if this cost of hydrogen would be around 3 euro per kilo? No, Stefano. So I think we have the possibility to see how this process can be really feasible in terms of financial numbers. And this is really the starting point of our story. It is not the end of the presentation, it is the starting point, because in INNIO, in Jenbacher, we have the capability to run through this kind of simulation. So we can also get the support from an academic point of view in order to bring us to the direction that is needed, and in case we can come up to a financial viability of an interesting operation or a business case. So what we have done, just to finish, is a comparison with the battery. Because one can say, okay, even if maybe I have the grid, but maybe I just want to have a backup during a short period of time, maybe during the summertime, I will have a rush of people that will go on vacation. Everybody wants to make EV charging at the same time. So maybe I just put a backup battery that can support me, for example, for the weekend. So we assume 72 hours grid outage. How much does this backup battery cost? Assuming that I have the space on the station to put these backup batteries, but very easily for a 15-year period, to just have a battery for 72 hours, this would cost 4 times the cost of the entire hydrogen solution that we have seen before. And the hydrogen solution that we have seen before could cover the complete charging station for all the hours that is needed, and not only during the outages or during the weekend. So this is also another thing to reflect on the battery as a solution compared to hydrogen as the storage. And let's say to wrap up, we have been starting with the problem of the grid support, and we are starting with the problem to see how we can solve the problem of the grid and how we can, let's say, leverage the development of the EV market. And then our, let's say, work was to study scenarios, to make some calculation, to see how we can optimize the processes, how we can use the heat in this kind of situation, and how we can analyze which kind of incentivization must be used. So what is the final message? The final message is that there is no one solution that can be applied in every place. In every kind of situation, you have to make cost analysis, simulation, and we need the sophisticated tools in order to perform this kind of simulation scenario, because there are a lot of calculations to do in the background in order to really understand what is the best optimization for each process. And with that, I think is the end of our presentation. So it's already 45 minutes. Thanks a lot for everybody that has the patience to stay with us all this time and listen to us. And we would like to show you where you can download our white paper here. So here you can use your phone and scan the QR code. If you want to do, I encourage you to do the survey. This QR code will bring you to a Microsoft Forms where you can do an anonymous survey, or if you want, you can leave your email address in case you want to be contacted by us to proceed with any kind of discussion that you would like to have with us. And I think it's time to the Q&A session.
Yes, of course. Thank you, Andrea and Stefano, for your informative presentations. Now let's dive into the Q&A session. Now, a quick reminder for our audience: to ask questions, simply use the questions widget. Just type them into the box at the top left-hand corner of your screen and click submit. Now, we've got some interesting questions already, so let's kick things off with this first question. What is the cost of 1 megawatt unit using 100% H2?
Stefano, I think I can take this.
Yeah.
So in terms of cost, I would really like that we can discuss this in a more detailed way, because, what I can say is that there is not much difference between natural gas solution and a hydrogen solution in terms of price, in terms of capex, and as well in terms of opex. So the number depends on the scope of supply. So, I mean, if you want to have more details, I encourage you to get in touch with us, so we can provide you a detailed answer.
Great, thank you. Now on to the next question. This is a two-parter, so I'll ask it slowly. What are the electrical and thermal efficiencies of combusting hydrogen? Are these percentages linearly related to the portion of hydrogen combusted?
Stefano, do you want to?
Yeah, I can give
your
a more
view?
academic answer for sure, but I think it's more straightforward to the performance of Jenbacher engine. But the point is that, of course, there is a big difference in the performance compared to natural gas when you go on blending of hydrogen into methane. That's because, of course, there is different kind of volatility of the flame, and substantially the blending effect has an impact on the combustion performance. But Andrea, you can give, if possible, more details on.
Yes, so for the engine that we have been using here, the electrical efficiency is around 40%, and the thermal efficiency we have tried to maximize as much as possible, and I think we were more than 80% in total. So we were using most of the thermal out of the engine, so we had the exhaust gas that has been recovered, so the thermal from the exhaust gas, and as well the thermal from the engine cooling water system. So in total, the percentage are not connected to the hydrogen. I mean, the combustion of the hydrogen is bring us to this 40% when the engine is running at full load. And if you think it's very comparable to the efficiency of the natural gas engine.
Thank you both. Let's dive into another question. Do you think that the electrification of cities in Africa makes sense with hydrogen, day plus night?
I could start to say that the electrification is not a process going on in Africa, but is a process going on globally. So every city is facing this problem or opportunity. I would say more an opportunity, because hydrogen will be one of the solutions and will not be the only one solution, because there will be overall global, let's say, asset in terms of renewables connected to the grid. but these renewables need to be stored somehow when there is not the renewable, because the renewable is not a source of energy that can be programmed. So you have it when you have it, and it is not matching maybe the demand. So the solution is really to find a way, the optimal way to store, and this goes to the slide of the storage solution that Stefano showed us before. So depending on the kind of application and the kind of storage capacity that you need and the discharge time that you need, you can find different solutions technically. What we think is that the hydrogen and the natural gas will be the good one for the seasonality and for the longer discharge time and the bigger storage capacity. Right, Stefano?
Yes, that's correct. And maybe something that we can add to give a holistically reply to this question that is interesting is that there are two main parameters affecting the answer to the question. One of it is the capacity, the size of the city that you would like to electrify, because of course, as mentioned before, the storage capacity play a significant role in the infrastructural cost of the energy transition. And when you look at large cities with large seasonalities, clearly, as mentioned before, a solution based on battery cannot be viable, because battery can be put in modules, let's say 1 megawatt hour to up to 10 megawatt hour. Then you have to take care of the thermal management of the battery, while when you deal with hydrogen or with synthetic natural gas, the thermal management part is reduced. And furthermore, you have to consider the fact that an energy carrier is much, would say, maybe adaptable to supply different kind of end user demands. So in the sense that it's true that you can electrify, but somehow if you think about heating system or cooling system, eventually, as for the case studies we presented, by burning hydrogen with high efficiency cogeneration solution, you can also generate heat, low-grade heat that you could have generated also with heat pumps. But in this case, you don't need to electrify. You're already using the hydrogen for the main supply of the electric vehicle infrastructure. So it really depends on the case scenario you would like to tackle. And my reply would be that, of course, there is rooms for hydrogen to be interesting support in energy transition and electrification for large cities also in Africa.
Great. Well, thank you for that engaging question and answer. Let's proceed with the next one. If running on 100% H2, how much O2 is necessary instead of air with 1 megawatt unit to prevent making NOx?
That's a good question. Let's say the combustion engine needs air in order to make the combustion of the hydrogen. So combustion of hydrogen and oxygen into the combustion engine is not something that we are currently developing.
Great, thank you. Let's move on to the next question. Can you please comment a little bit more on why you assume to use trucks for the H2 transport from the generation point towards the charging station?
Yeah, the assumption, Stefano, correct me if I'm wrong, was that our, let's say, faster solution, because here we are thinking that we want to increase the market of the EV charging, and we don't want to wait for the infrastructure to be ready. So we don't want to wait for having, for example, a pipeline for hydrogen. It will come maybe in some years, but not next year. So if we want to have more charging stations with fast charging for the trucks and so on, we need to bring the chemical energy stored in hydrogen to the point of use in the most effective way. And for 100 of years, we have used the trucks to bring the oil from the refinery to the fuel station. So this is the fastest and more common way to bring the energy from one side to the other. And in our view here, maybe is a little bit limited to a small world, but if we enlarge a little bit our vision and we think about the green ammonia system that, for example, I know that there are people from Chile listening to us today, and I know that the Chile is developing solution, but not only Chile, of course, to produce clean green ammonia and transport this ammonia through the infrastructure of the existing ammonia already to other countries like Europe, and provide this ammonia with a price which is really something very, very cheap, and really makes sense even more, because then I can transport the ammonia to the port, to a port close to the charging station, and then I can transfer this ammonia from the vessel, from the boat, to the truck, and bring the clean ammonia to the filling station, and then I can maybe separate the ammonia into nitrogen and hydrogen, and bring the hydrogen into the engine, and that's the same thing, but we change the way that we transport the hydrogen from one side to the other. So at the end, if you change, let's say, the numbers of the viability of the solution, you can also have an easier solution to the problem.
And if I can just add one thing very quickly, layman consideration, very often from the financial perspective, you install renewable energy field like wind farm or PV farm remotely where the cost of the land is cheap, and to bring the infrastructure to the pickup point is not that easy. So that's why truck in this, let's say, short-term transition, as Andrea mentioned, could become something more effective in terms of quickness of introduction.
Thank you both for your great answers. And let's keep the momentum going with this next question. Okay, so it's a bit of a long one, so I'll ask it slowly. The current cost of produced energy seems not very competitive, and you are assuming that it will get eventually better with future incentivization schemes. However, grid electricity prices are likely to decrease as well in the future due to high renewable penetrations. Furthermore, the energy deconversion chain is not favorable in your H2 based proposal. Can you please comment more on that, and what could be other competitive advantages of your solution?
Well, if you want, Andrea, I can start to answer the
Please.
question. Yeah, thank you for the audience for the interesting question. This is a very good point. So I will start from the bottom. I think that the most important thing is that if we look at the decarbonization process, we cannot continue to use the same metric of thinking that higher efficiency is the solution. We need to start to look at the perspective that emission factors characterizing the generation of electricity or alternative of different kind of energy form like heat and cooling become the weight of the optimization process that allows to understand which is the better pathway to achieve decarbonization. So from this perspective, yes, it's true that on the efficiency side, the conversion that we propose is low because we have all the chain from PV till hydrogen, but it's also true that we are able to generate electricity at fast charging station in a city center, for instance, with only 6% of the overall emission that would have been happening if the electricity would have purchased by traditional grid solution characterized by, let's say, 0.3, 0.35 kilogram of CO2 per kilowatt hour of electricity. And this is already including the penetration of renewables in the grid. Second part is that the cost of the electricity, I'm not so sure that it's going to draw to become lower in the next future, because it is proven that let's say the slope, the derivative of the penetration of the renewable in the electricity grid is not anymore so deep. So I'm not so sure that the increase of the renewables, we can think about Italy, we are from Italy, are going to be so relevant on a marginal perspective on the penetration. You consider that today we have 8% to 15% renewables in the energy demand supply in Italy. So even if we double it, you still already have a 15% more to develop. So I don't think that the weight itself make the comparison viable. And the other thing is that we are comparing two different kind of utilization of the renewable. Here is the idea is that you can dislocate the renewable from the infrastructure and that you can serve very niche market that is growing fast and have a quick response to the market needs. Plus, the solution proposed is modular and can be dispatchable in different parts of the country. So you are independent from the infrastructure. I would see that in that way. Andrea, please feel free to add.
No, it's exactly what I would say, because if we look to this graph, I mean, if we compare to the 0.09, of course we are not competitive. But here we are talking about again a 125 kilowatt charging station, and if you go to a ultra fast charging station, assuming that you find one in Italy, but I have friends that are paying around €1 per kilowatt hour already today in the public fast charging station. So it's not far away, and they don't know if it is a green energy or a gray energy. So here we are talking of a green energy solution with a price which is comparable to what is the price already today at a charging station in Italy.
Yeah.
Thank you both for your amazing answers. So I'll ask this final question before I conclude this Q&A session. What is the difference between 1 megawatt hour energy saving capacity in battery or in hydrogen?
Sorry, okay. What is the typical hydrogen supply? No. What was the question?
I think this is number 12. What is the difference between 1 megawatt hour?
Energy saving capacity in battery on hydrogen.
So I would say that I can guess that what is meant, which is the storing capacity in battery and hydrogen. So, well, the main difference is that the energy content is the same. The difference is that in this case, 1 megawatt hour capacity battery has a, let's say, round trip efficiency up to 90 to 92% when taking into account latest lithium battery solution. But it's in hardware, so you have the physical hardware to be located, connected to the grid, and powered by the grid. The content of 1 megawatt hour in hydrogen means that if you divide by 33.3 roughly megawatt hour for low heating value of hydrogen, means that you have more or less 30 kilos of hydrogen that you can bring with yourself in a small tank, and you can use it wherever you like. Of course, there is a discharge efficiency in this case, if we want to use a similarity to battery, that depending on the energy converter technology can be lower, but you save a lot of costs in terms of the investment compared to the battery, because you are dealing with the energy content of an energy carrier. Andrea, I don't know if you would like to add something on it.
No, I think it's very clear.
Well, fantastic. Excellent responses, Andrea and Stefano, and thank you both for your informative answers. As we're over our scheduled time, we'll have to conclude our Q&A session, but please don't worry if your questions haven't been addressed yet, as our speakers and team will follow up with you. And that brings us to the end of our Q&A session and webinar. I'd like to express my heartfelt thanks to Andrea and Stefano for their outstanding presentations, and to our sponsor, INNIO Group, Jenbacher, for making this session possible. To all our attendees, keep an eye out on your email for instructions on accessing the on-demand version of this webinar. Don't forget to check out the related resource widget for more helpful materials, or scan the QR codes on your screen. We'd really appreciate it if you can take the time to fill out our surveys. And that is it. Thank you for joining us today, and I wish you all a wonderful day ahead.
Thank you.